Hi, everyone. Welcome to the Virtual Eclipse Community Meetup. Virtual IoT Community Meetup. I'm here with Christian and Simon, who created the Eclipse project, Eclipse Mita. It's a language for embedded IoT, and they're here to talk to you all about it today. If you have questions, remember to ask on Twitter, #VirtualIoT, or on the YouTube channel, and Simon and I will be monitoring that while Christian talks. Go ahead, Christian.
Hi, I'm Christian, and I suppose we dive right in. So let me share my screen. There we are.
Looks good.
Cool. So yeah, today's about Eclipse Mita, which is a new programming language for the embedded IoT. And before we dive into all the details, let's have a first look at it. What is it actually doing, and what do we mean when we say embedded IoT? So let's suppose we wanted to create a simple shock detector, a device that, if dropped, would use an accelerometer to detect that event and then send it out using Bluetooth Low Energy. So we're actually going to write code straight ahead, and this is not intended to sort of give an in-depth look into all the features, but to give you a rough feeling for how Mita looks like and what you can do with it. So Mita itself is an event-based language. And there are different kinds of events available on a system. Time is an event too, so I can do something like every 100 milliseconds. In this case, for example, I want to read the accelerometer magnitude and check if that's greater than some threshold. And this is going to be my shock criterion. So if my acceleration is too large, we say this is a shock. And now I want to do something with that. For example, I want to send that out using Bluetooth. So I have to set up my Bluetooth on this device, give it a name, call it smartphone. And then here I have different resources available to me that I can set up. Bluetooth in this case. I can configure this Bluetooth device. I can set the device name, for example. And I can use, in Bluetooth, they're called characteristics. You can think of them as some sort of signal that's sent out. I'm going to call that shock detected. It needs a UUID. Like that. And now I can write to that. And that's pretty much it. Right? So if I hit save now, what happens in the background, we get C code generated that implements this program on a device called the Bosch Cross Domain Development Kit, or XDK for short, which, among other things, has an accelerometer and a Bluetooth radio. We can look at that code, or better, this one. And as you can see, this is fairly readable code, fairly readable C code, but it's also plenty of it. And if we were to flash that to the device, which I've done here. There we are, the device is flashing. I hope you can see the video. Then at some point, it's going to show up in this generic Bluetooth app that we have, BLE smartphone. We didn't give it a name, so I choose one. We can look at the characteristics, read that, and when we shake the device, sort of induce a shock, then we get the notification. This demo also has additional functionality where if the button is pressed, the shock event is reset. All right, so in about 10 lines of code, we implemented a pretty simple program, but given what's going on behind the scenes in terms of configuring the Bluetooth stack, configuring all the I/O pins in the device, etc., it's still fairly complex. So that's sort of what Mita does, is it encapsulates this complexity, which makes it accessible for beginners, but at the same time, it generates C code for a production-ready C code for a target platform so that you can carry that over into actual product development. Let's take a quick step back and look at why is this actually something that we would need? Why do we need a new programming language? I mean, this is not an obvious thing to start with or do. And when we look at the Internet of Things, what we find is that we really have two worlds almost colliding. On one hand, we have the cloud world, where we're talking about giga and tera in terms of size, gigabytes, gigahertz, virtually unlimited energy and anything really. And on the other hand, we have the devices, which in their most extreme form have a few kilobytes of RAM or flash, are battery powered and thus have energy constraints that we need to pay attention to, and are just programmed completely different. And now in the IoT, those two worlds have to come together somehow. And this creates a problem, that there's a barrier in between those two. And at the same time, on the lower end of things, so to speak, on the device side of things, what we're seeing now is that in the past, if you wanted to scale over quantity, that really had a few steps that you needed to take in order to be able to do that. So for example, if you built 1 to 10 devices, you would sort of solder something together or stick it together on a breadboard. Most people who will have played with the IoT will have seen, say, an Arduino with a breadboard and some wires going from that. And that's good for first prototypes. But every additional unit you want, you need to build yourself, and every time you incur effort. And so at some point, you'll start building your own PCB, your own circuit board with components on it. And that is fine up until another sort of, say, 100 devices or so, at which point it will make sense to look into some cost down and get that manufactured elsewhere. And then if you're looking at industrialization, meaning actually selling a product, you're facing an entirely different set of barriers. That is, for example, certification, CE, FCC certification, or the Radio Equipment Directive in Europe. And for all those certifications, for example, you'll want to be really, really sure that you know what your device does. The same goes for when you have that in the market, because once you have 10,000 devices out there, updating them is really difficult. So, but in terms of hardware, we've always had these step functions. And what we're seeing now is that this curve is flattening out on the hardware side of things. And that is because what we're seeing is a sort of set of universal hardware that is coming to the market. So I've already mentioned the Bosch cross-domain development kit, which has 8 sensors, a battery, Bluetooth, Wi-Fi, and if you need 1,000 of them tomorrow, you can have 1,000 of them tomorrow. And we're seeing that in similar hardware from other manufacturers as well. And so what that does is it basically means that for a lot of space in that sort of quantity scale, you don't need to build your own hardware. And yet, in terms of software, this is because we basically have everything in those devices that you might possibly need, right? So there are a lot of sensors in there, there's radio in there, and these feature sets and what those devices have in them differs across manufacturers. On the software side, though, we're seeing that we're not scaling just as well yet. So in the 1 to 10 scale, you would start with something like Arduino, and then later, once you go to sort of the 10 to 100 side of things, you might need some more efficiency. So you're more likely to look at vendor libraries like STM32Cube and stuff like that. Eventually, testing will play a bigger role because you have more and more devices that you need to manufacture, and so you need to make sure that they actually do what you want them to do. So end-of-line testing and stuff like this becomes more interesting. And lastly, when it comes to certification, not only will you need particular features, which you're unlikely to find in sort of the prototyping libraries, as well as you need to be really, really sure that your device does what you want it to do. So you'll need a lot of control over the software in your device. And so out of those two considerations, like that we have people coming from a cloud sort of world that want to program embedded devices, and at the same time, the scaling of a quantity from 1 to 1,000 devices, we found that in the embedded IoT, we really need a way to program that lowers barriers for people, that something that is feels familiar, that is easy to learn, that feels good. All of the fairly soft targets, right, which also means that they're hard to reach. things like convenience matters. So if you need to spend 800 lines of code and a lot of documentation reading just to get a simple signal out over Wi-Fi, that's difficult. And at the same time, we don't want to annoy power users. So if you do know how to sort of get in the engine room, so to speak, and really fiddle with all the knobs, we still want to have that available to you. And then the second point is exactly that we want to be able to scale to production. So on the lower end and the low quantity range, we want a lot of flexibility. We want to be able to try things quickly. At the same time, we want to have a lot of trust in our software. And that starts with timing behavior, with memory consumption, with the way our software actually does configure the hardware, which also has an impact on certification, for example. So that also means that we want to rely on proven infrastructure, on tools, particularly when it comes to debugging on the embedded side of things that have proven themselves. And lastly, we want all that on really low power hardware. So when in the sense of Mita, we're talking about embedded IoT, what we mean by that is sort of the Cortex M0 to Cortex M4 level, right? On Cortex M0 to M4. We're not talking about something like embedded Linux or anything on, say, a Cortex A level and up. So we're really talking about sort of mixed signal microcontrollers, possibly an MSP, something like that, right? Low power. So that also means that we cannot afford a lot of performance impact at runtime, which means that garbage collection is out of the window, and we need some well-defined resource management. So with this sort of catalog of things that we would like to see, how do existing languages stack up? Why not use something that's already out there? I mean, implementing or designing a new programming language is not an easy or obvious thing to do. And there are a few candidates that we might want to look at. For example, JavaScript or Lua. Lua was specifically designed to be embedded into C programs. There are implementations, embedded implementations for JavaScript, for example, duct tape, that run on 300 kilobytes of flash. However, what those languages do is they remove us yet another layer from the hardware that we run on. And when it comes to understanding their behavior at runtime or the way they configure hardware, that can be really difficult just because there's this sort of black box layer that is introduced in between. There are other languages, dynamic languages most notably, which target embedded specifically. For example, MicroPython or mRuby, the latter invented by no one less than Mats, the inventor of Ruby himself. And while those languages work for a lot of use cases, particularly for prototyping, they are dynamic languages at their core. So they come with a memory penalty. They come with a performance penalty at runtime, which means that, for example, keeping hard timing requirements can be difficult. So if an interrupt happens, you want to react to that, and in just this time you need to garbage collect. You might have already missed your time slot. Then there's a separate set of programming languages and libraries that are worth looking at, most notably C++, which is a question that comes up quite often. Why not use that? C++ has a lot of accidental complexity that make it really hard to write memory-safe programs, particularly on the embedded. Rust is a really interesting contender in that space, and the Rust embedded working group is just forming or has formed. But even there in Rust, we get a lot of nice guarantees, yet, for example, the event-based programming style that Mita offers is not found in there. Then there's Arduino and Mbed, which are both based on C++, and so we end up in that corner again. So let's look at Mita. What does Mita do? So until now, we wrote mostly C code, compiled that, and flashed that on the device, or on a device. With Mita, what happens is we write Mita code, which in turn compiles or transpiles to C, and we flash that on the device. And this is an approach that we have seen a lot happening in the web world, where, for example, TypeScript transpiles to JavaScript, which then runs in your browser. And Mita does a similar thing, where you write Mita code, which offers feature set richer than what C does, which transpiles to C and then runs on your device. The difference here is that the code that Mita generates is explicitly meant to be read and or modified. So what we try to do is to generate code that looks, in the ideal case, as good as if a skilled C programmer had written it. This is a high goal. We don't always reach it, but this is what we strive for. So Mita itself is an event-driven language. We've already seen that in the demo in the beginning. This has the great benefit that this really matches the way IoT devices work. Most of them are battery-powered, at least ones that we target with Mita. And so they'll spend a lot of their time sleeping, wake up based on an event, do some computation, maybe communicate with the rest of the world, or an event might also be an incoming packet from something else outside, and react to that and then go back to sleep. So we always have that sleep, have some event handling, and then go back to sleep. And we directly translate that into the language. Then we also have a form of automatic memory management, where we try and compute the memory that we're going to need statically. So all memory in Mita is statically allocated. This has a lot of benefits. For example, at compile time, we know whether our program is always going to fit into RAM or not. It also has disadvantages. It limits things that we can do. For example, a linked list is not something that you would sensibly want to write in Mita. I mean, you could do that, but you would need to know how many elements are in that list, which kind of defeats the purpose. Mita is also completely statically typed, meaning that really every expression always has a type. There's no such thing as an any type or a void pointer or anything like that, which also greatly improves the quality or of the programs that you'll write in Mita. Then you get direct access to system resources. Again, we've seen that in the demo, where we had direct access to the accelerometer data in our code. And at the same time, we have a declarative setup where we can configure the system resources that are available to us on that specific piece of hardware that we're writing code for. And the difference here compared to how this is traditionally done, where you would have some initialization code that gets called at startup, is that this is based on a description of the hardware. So this is really a kind of model-driven configuration in the beginning, which also means that we can validate the configuration before we bring it to the device. So for example, if you have a sensor which has several configuration items that you can change, some of which combinations are invalid modes of the sensor, we could tell you that as you write that in your configuration. And lastly, as already mentioned, all of this transpiles to C code, which also means that not only can you inspect that C code and learn from it. So if you're interested in how to use, for example, the vendor libraries that ship with a microcontroller, you could look at the code that we generate and learn from that, sort of as an interactive example generator. But it also means that once you hit the glass ceiling, once you hit something that you cannot express in Mita, you can swap over to the C code and continue there. Additionally, the foreign function interface towards C that we are able to offer is native, just because we do transpile to C. So let's have a look at Mita up close. On the left, you see a first example of Mita code, and when you just look at that and just glance over it, it shouldn't look all that foreign. There's a lot of things that you will have seen before, particularly if you've code in something like TypeScript or Scala, Rust, Swift, Go, those kind of languages. So first of all, we have all classic control structures, no surprise there. We have mutable and immutable variables. And for us, mutability is an important concept because it really helps optimize the generated code. And lastly, we have static typing with type inference. So the two variables there, they did not have an explicit type, but we were able to infer that. I mean, in this case, it's trivial, but this also works for more complex statements. So again, all expressions have a type at compile time. Now, Mita itself is not object-oriented, but we have something that you'll know from other languages too, which is called extension methods. And basically what that means is that the first parameter of a function can be written on the left-hand side. So instead of mean of values, we can write something like values.mean. And this really gives the language an object-oriented feeling. You can think of that as something similar to Go receivers, or if anyone's written code in Eclipse extend, extension methods work exactly the same way. And in Mita, functions are polymorphic, which means that you can have multiple functions of the same name but differ in their signature. And this way, you can really implement sort of, or really get an sort of object-oriented style back in your code. The standard library is actually implemented that way. So the self.length that you see used in that function above is actually a standard library call, and it's just an extension method on array. Then we have static memory management built in. So as an example, here we're doing some string interpolation, also a feature of Mita. It uses the TypeScript syntax for that. And as you can see, we are computing, on the right side, you can see that we are allocating enough space for that string to fit in there, including the temperature value that gets interpolated in. And we can do that because we know how wide a int32 value can be as a string. So this is basically a worst case analysis that happens here. This also works if you return things from a function. So if someone were to call build message, the build message function that we see here, if someone were to call that, what we would do is we would be able to analyze how much memory we would need for that function, allocate enough memory on the stack, and pass in a buffer of that size. Sort of the way a C programmer would naturally do that as well, except that we do that for you. Yeah, here's the example of what I just said. We are computing that we need 23 characters, so we create the space for that on the stack and pass that into the method. So that's sort of a brief overview of the imperative side of Mita. There are a few surprises there. What's more interesting is the declarative system setup. So in order to be able to run code on our embedded device or to interact with the outside world, we need to configure that device. So for example, we need to configure the radio, for example, Wi-Fi or Bluetooth or LoRa. We need to set up our application level protocols. For example, we want to talk MQTT over Wi-Fi, we have to configure that. And say we use a general purpose I/O pin for reacting to an event, also that we have to set up. And so all those things that we can set up are considered system resources in Mita. Exactly, sensors, connectivity, etc. And those resources have configuration items. Again, we've seen that earlier in the quick demo where I set up the Bluetooth resource and there was an advertising interval or a device name configuration item which I could set up on Bluetooth. All of those resources can also offer events. So for example, most modern accelerometer will be able to trigger an interrupt if they detect activity or free fall or something like that. And these events can be passed right into Mita as well. And those resources offer modalities, which is basically state that changes at runtime, most notably sensor data. So, for example, the temperature on an environment sensor would be a modality that you can. And all of those resources are described for a particular platform that we want to write Mita code on. So at the moment, Mita supports, in terms of platforms, the Bosch cross-domain development kit. And we have a sort of very first prototype of an Arduino board, mainly intended to show how a very simple platform would look like. And we're always open and eager to support more platforms. So if anyone's interested in supporting Mita on their platform, we are very happy to help there and to give support on it. So once we have that platform description, we can make use of that, and we can set up those system resources. All setup starts with the setup keyword, followed by the name of the resource that we want to configure. And then there are those configuration items which we can set. We've already talked about them. So in this case, the accelerometer has a range in which it can detect acceleration and has a no motion threshold at which it will trigger a motion event. Some system resources can also be named. So, for example, the WLAN or Wi-Fi system resource can be given a name so that it can be referenced later. So on the left side, we're setting up the Wi-Fi resource, and on the right side, we're setting up the lightweight M2M or a lightweight M2M protocol stack, and that needs to know through which device it should talk to the outside world. And so here we just pass in a reference to the Wi-Fi that we've set up prior. And what Mita will actually do is it will compute the order in which those resources need to be set up based on their dependence or dependencies that they have with each other, and initialize them in the right order. Lastly, what we see down here is a shock detected. And this is what we call a signal. And signals are basically communication channels with the outside world. And what particular signals are available to you depends on the resource that you're currently setting up. So in case of lightweight M2M, we're talking about properties. In case of Bluetooth, GATT, we're talking about characteristics. In case of REST, we're talking about resources. In case of GPIO, we're talking about pins, right? And those signals really look like constructor calls in a way, and are basically are instantiated in the sense that here we are instantiating a property signal, which we call shock detected, that we can then later read and write from. We've also seen that in a quick demo in the beginning, where I set up this shock detected signal that would send out something over Bluetooth. As I already said, every system resource has its own signal. So in this case, for example, the GPIO system resource has a digital out and an analog in signal that we can use. Anyone who's used Arduino before will find that familiar. Or down below, there's the I2C resource where we can map registers in directly and start reading from them, or write to them, for that matter. Then we have direct access to sensor data. So, for example, if I wanted to read the accelerometer magnitude, I could just do it that way. And then all the setup that's necessary to do that, and all the sort of works and plumbing that has to happen before this can take place is sort of hidden away from me. I mean, I can see that when I look at the generated C code, but in Mita, I do not. And which also means that I don't have to care about that, right? As a programmer, what I want to express is my intent to read the sensor data here. And the fact that this uses I2C is something that I do not necessarily care about. And lastly, as already mentioned, Mita is event-driven. So there are different sources of events, timers for doing things repetitively, but also from all the other resources. So for example, sensor data or when the system starts up. And the way Mita implements those events is that whenever an event happens, it gets put in an event queue and executed sequentially. This has a few benefits, most notably that we don't have to worry or deal with different execution contexts. So all your code will always get executed in the same context, not, for example, in an interrupt service routine context. And it also means that we don't have to worry about concurrency simply because there isn't any. The disadvantage of that is that you don't get strict timing requirements at the moment, because it's possible that there's an event handler that's running before you right now that takes a long time. So those are out of the window at the moment. All right, so to wrap things up, briefly another quick example of some Mita code. What we do here is we have a program that every 10 seconds sends out acceleration and temperature data as a JSON string using MQTT over Wi-Fi. Right. So when we look at this from the end towards the beginning, we see that event-based programming style, where we do something, for example, based on time. We have imperative code that looks very similar to modern dynamic languages, in this case TypeScript, where we also get things like string interpolation, or we can just return strings and we don't have to care about all the memory management. And we have the declarative system setup that configures our system beforehand. There are a lot more things that we haven't spoken about yet. There are packages, there's exception support, and more in the platform support than what we've mentioned. One important thing to note is those 29 lines of Mita code that we've just seen, they transpile to 842 lines of C code. And this sort of expansion ratio depends on the quality of the generators. And it's not just because our generators are pretty good at this point. It also depends on how the API for the platform that you're generating code for is designed. But the takeaway message here is that Mita code is very concise and is meant to express the programmer's intent very well. And even if you're able to write those 842 lines of C code, that doesn't mean you necessarily want to. So chances are, even if you're a seasoned embedded C programmer, you might want to start with Mita just to get the scaffolding out of the way, and then dive back into the C world that you already know. So to sum up, Mita is a new programming language for the embedded IoT, which enables high-level features that are transpiled to C, and it is open for everyone. We're proudly an Eclipse IoT project, and if you're interested in getting engaged with Mita, we are on the Eclipse Mattermost, or come and find us at mita.io. Thank you very much.
Thank you, Christian. So Simon answered all the questions already. Thank you, Simon. We have no other questions, so I think there's a little echo, but do you know of any use cases where it's used in the real world already, or is it going to happen soon, or what's the timeline for it?
So it is shipping as part of a commercial offering by Bosch.
Okay.
So Bosch, who offer the Bosch Custom Made Development Kit, that toolkit that we saw in the beginning of the presentation, ships with a Eclipse-based IDE called the XDK Workbench, and Mita ships as part of that workbench. So when people do prototyping with the XDK, they also do use Mita for that.
Okay, cool.
So it is actually used in the real world.
That's awesome. If you have other questions, you can answer them now. I'm just going to share my screen and do a few announcements, and then we'll check again. So I just want to tell you all about a few things before we go. We do have an Eclipse IoT Day Singapore happening very soon in September. We are currently accepting call for papers, so if you have a talk and you want to be there, just submit one. If you want to attend, you can also do that. It's 249 euros, US dollars until August 24th. And we also have the latest Eclipse IoT newsletter. It just went out. You can view it by going on our website and just clicking here. So that's it. I'm going to stop sharing and see if there's more questions. So there is a question. Is there a link to all supported platforms devices that is updated?
So on the mita.io website, we do have a list of platforms, which at this point is fairly short. It's literally 2 if you don't count the unit testing platform. So that's on the website, yeah.
Okay, perfect. So thank you so much for joining us today. Thank you, Simon, as well, for answering all the questions. This is my last virtual IoT meetup. I'll be leaving the foundation on August 17th. It has been great. I love doing this and chatting with all of you. You can follow me on Twitter at @RoxaneJonka if you want to stay in touch. And we have a next meetup coming up on September 5th with Sci5. And we have 5 lined up until October, so we will be around. So thank you, Christian and Simon, again, and see you, everyone, in the fall.
Thank you for having us.
Thanks.
Bye.
Bye.